Hello, my name is Stachniak, and I'm the dev lead on the Microsoft Mixed Reality Scene Understanding team. The title of my talk today is Digitizing the Physical World. So what will you learn in this talk about scene understanding? First of all, I'll sort of walk you through what scene understanding is and what it can be used for. I'll give you an overview of how applications interact with the scene understanding runtime. We'll start looking at some core concepts and core components of the scene understanding runtime as it is today. And then we'll walk through some examples of how you build different types of applications with scene understanding, which will hopefully clarify a lot of what we'll learn in the earlier parts. And then at the very end, I'll sort of walk you through everything you would need in order to get started if you're interested in getting started in scene understanding. So this is a snapshot of something that we call the spatial mapping runtime. And it is the first environmental representation that we had in HoloLens 1. It is similar to things that you are seeing now on Apple's iPad with our LiDAR. And it is essentially this idea of integrating the depth signal that you get from your device. So you're constantly accumulating more information as you see it and building up this dynamic mesh. It's got some wonderful properties. So, it updates this room in real time. It's used very successfully in things like occlusion rendering, where you want to render a hologram in the scene, but you want the hologram to sort of be occluded by certain parts of the geometry. You can essentially render this mesh from the viewpoint of the camera, and then your holograms will occlude correctly. But it is also a very hard representation to use if you want to do some higher order things. So like, what are some of the limitations? First of all, it's constantly being updated. So it's a bunch of triangles that you have to sort of sort out in real time. As you can see here, for instance, there are holes in this mesh, and they don't necessarily come from the fact that you haven't just looked there yet. This chair, for instance, is occluding this mesh, and no matter what, it's going to be very hard to get data here. You also don't know what's what. So, for instance, this is a chair. Here we have a bed, but predicting that and having characters interact with your space is something that we sort of left to the developer to do. So we started talking to our development partners, and it sort of led to this vision statement that it's currently unintuitive to write mixed reality apps that interact naturally with the real world. The problem statement itself is relatively simple and straightforward. The question is, well, what would an intuitive environmental representation look like, and how do you build one? Luckily, we didn't really have to invent anything. If you look at the gaming industry and potentially even the animation industry, there have been a number of paradigms established for environmental representations. There are a lot of algorithms that people have already written that make environmental processing quite easy. And so really the problem became, how do we start to take what we started on in this journey with spatial mapping, with these mesh representations, and turn this representation into something that looks much more similar to what a game would see. So here is an image of what a game would see as part of your environment. So some things should naturally stand out. So as you can see, for instance, there are objects in this world. They seem to have some sorts of spatial relationships. You can see bounding boxes on them. Presumably, they have various representations and geometries, some that make collision simpler and faster, and some that make rendering better. There are lights in these environments. There are materials. They are part of a scene graph. These concepts just are ubiquitous in these 3D applications. And so scene understanding was sort of birthed from this idea that, well, let's take what we know in the space of deep learning, let's take what we know in the space of computational geometry, and let's take the great work that we've done in spatial reconstruction and spatial mapping, and let's build environment representations that look like this, and in a sense digitize your environment into something that your application can understand. Okay, so this is a view of the scene understanding runtime, or at least how your HoloLens sort of perceives a room that you requested. And as you can see, it looks very different than the mesh representation. This is actually captured from our sample app that at the end of this talk, I'll tell you how to download and run, and you'll be able to see this and play around with it yourself. But with the scene, I think I can show you some of the core properties of the scene understanding runtime and walk you through them. So the first thing is something we are calling object decomposition, and it's a very simple thing. It's just this idea that we no longer have dynamic meshes that are always updating, but we have objects that are tracked and persist over time. You can see like there's a platform here, and there's a wall here, and not only are they selectable on the bounding box, so you can see in Unity, for instance, they are rooted to the root node, and there's a scene graph of all these objects that you have in your scene, right? And so you can now sort of reference these, and we don't go into too much detail in this talk, but as you update your scene data over time, you will be able to refine the wall, and as it updates, and it persists as the same object, for example. So this is a very key property, is this idea of we are now decomposing the world into specific objects that may or may not have multiple representations. The next key component is something we call the watertight manifold, and it's tightly related with something called semantic completion. Let's start with the watertight component first. So there's a large class of algorithms, and as if you remembered, we started talking about this concept of there exists a slew of algorithms already that process environments, and some of the core ones are navigation and physics. And navigation and physics, they don't need to, but they love watertight meshes. And watertight meshes, if you don't know the term, literally, if you took this room and you poured water through it, the water would not seep out. There are no holes in this room. Everything's connected. All the lines are connected. Why is that important? It's important, for physics, for example, which has raycasts as one of the core properties. It's important that as these rays bounce around, a ray never flies off out of the room into infinity. And navigation is another one. Yes, like there's a lot of work done on bipedal navigation for characters on things like floors. But if I want to have a drone that is navigating this space, it becomes harder, because if there's a hole in the ceiling, there's a hole in the floor, why wouldn't it not be a valid solution to go underneath the floor and come out the other side? So you'll notice that there are these sort of gray panels here. I'm just sort of marking them. These do not represent real geometry that we've seen, but they represent areas of the environment that you've either asked the system to sort of stop at, or where we don't have enough data to know what's beyond that. And part of the scene understanding runtime actually completes this as a separate object, so you can decide whether you do or not care about these components. But if you sort of sum up all of these, the walls, floors, ceilings, and these inferred regions, you'll get a watertight environment, and you can suddenly start doing real physics. I'll get a little bit later as to why that's even more critical, and why it's different than physics that you may have seen in other things like ARKit demos and AirCore demos, etc. The other one is related to semantic completion. You'll notice that there was geometry. If you remember in the previous slide, there were some shelves here. I'll sort of draw them, and a counter here, and there's extra geometry. This only renders the wall, floor, and ceiling. We never could see the floor here, and if you remember that old mesh where there was a chair and there was a light upside issue, we would sort of stop and only give you the data that we saw. But with scene understanding, because we sort of know that this is a floor, and we know what are not walls, we can sort of complete parts of the environment even below what's been seen. And so now our watertight representations are not only watertight, but they also complete, and so you can get a sense of the fuller structure of the room. Again, you'll see some demos of where that is, and it's not interesting. The next thing I want to talk about are planar surfaces, and this idea that objects can have multiple representations, which is something that's pretty common in these representations in gaming. So if you remember before, there were these platforms and these unknown planes that were very geometric, and now in this view, we replace them with another view of the same objects, but they are rectangular. And this is this sort of idea of taking these complex 3D surfaces and transforming them into 2D rectangles, if you will, on which you can do placement. And this idea, like, could you write mixed reality applications in 2 or 2.5D to make it a much easier development experience? And we'll walk through how these work a little bit later. The other thing that you'll notice, I think you've noticed them before as well, is this idea of semantic classification. So not only do you have these planes and these meshes and these components, but of course everything is labeled by what it is. So there are labels for walls, floors, and ceilings, and platforms, and unknown, which is the absence of any of those classes, so that you can start enumerating and finding things. So for instance, you could try to find like the largest platform and place a hologram on it, or things like that. Now, the very last concept actually brings it back full circle. I talked to you a little bit about the spatial mapping meshes, and that they're actually fantastic representations for some of the problems that we want to work on. Primarily, they have detail that planar representations do not, and they update at a different rate than scene understanding does. And so, in scene understanding, the spatial mapping mesh is actually a first-class citizen and a property, a component of it. So depending on how you request your data, you could actually see the mesh as well in your scene graph, along with your watertight manifolds and surfaces, etc. And so you can start combining these different concepts into building these richer applications. So for those of you who have worked on HoloLens 1, you may be familiar with spatial understanding, and you might be wondering what the difference is between scene understanding and spatial understanding. For those who don't know, so spatial understanding was a component that we had built for some of our interactive applications that had to deal with these environmental problems in HoloLens 1 timeframe. And we sort of productized it as a component that you could run. You essentially lock your spatial mapping mesh, and then it runs a bunch of processing on your scene, on the static scene, and tries to identify planar components and do some rudimentary analysis. Scene understanding it was heavily inspired by the successes that we had there, and it was built as a desire to have that as an inherent part of the system, much like spatial mapping is today. So we wanted it to be integrating data all the time. We wanted it to be doing DNN inference so that it could support much more complicated environments that have multiple floors or stages or split level rooms. And so in that spirit, scene understanding really it's a spiritual successor, because it's a new runtime that is part of the driver and sort of makes the spatial understanding runtime obsolete. But they do share a lot of commonality in terms of what their goals are. Now, scene understanding is not supported on HoloLens 1, primarily because we do use the on-device DNN, deep neural network chip, to classify the data that you see, and HoloLens 1 does not support that hardware. But conversely, for HoloLens 2, we did not port back the spatial understanding runtime, because scene understanding is an absolute superset of what you have there. On top of just planar decomposition and rudimentary analysis, it has all the stuff that I just talked about. Okay, we've seen what scene understanding is. Now let's talk a little bit about what scene understanding does. So the next part of this talk is going to show you a series of demos that should hopefully highlight what you can do with scene understanding in the augmented reality space. So I've scanned my environment, I have a watertight mesh of it, and I want to do some things. Maybe the first thing I would want to do is some basic physics. So here in this demo, I'm going to start throwing some cubes around, and you can see that my floor is planar. The cubes stay the same, they're nicely aligned. That's great, but how about we throw something a bit more interesting like the sphere, and you can see it bounces on the wall. These, because this mesh is watertight, I can throw more things. So here I just throw lots and lots of stuff in this. And so not only do I have the power of the watertight mesh, but I also start seeing this nice interaction between the augmented reality space and Unity, for example. So Unity, just knows that it has some geometry to collide against. It didn't know that it's my environment that this is happening in. But we're essentially just running the physics engine of Unity and then overlaying on top of the real world, and it just works. So while that was pretty cool, if you look at AR demos, you'll see quite a lot of demos that do similar things where you could do physics on planes or planar components, where the concept of watertight meshing and building a whole cell complex and being able to scan and update entire rooms is when you start doing it at larger scale. So here, like, I'm on the second floor, and I'm going to start throwing some virtual objects, and you can see, well, that's cool. They can like bounce around, but now like they can jump from one floor to another. I can do physics scales that we've never done in AR because I have my house essentially digitized in this representation. So now I'm just going to have some fun and just like throw a whole bunch of stuff there, and you can see that it's just interacting with my staircase and with the floor and on walls, etc. And I'm starting to see some of the true power that scene understanding provides. The next demo is something we call mini-map mode, and it's useful for visualizing your space or creating a mini-map of your view. It's quite easy to do. You essentially just take your scene, you route it to something else, something near you, and change the scale, and you can sort of just walk around and virtually see your space as a little dollhouse. It's pretty cool. One of the intriguing scenarios in augmented reality is this idea of reskinning my space and making it appear like I'm in a different place, in a different world. So with scene understanding, again, we have this watertight mesh, so everything is completely covered. And not only that, it's very easy for me to generate UVs to texture map my environment. So in this demo, what we call augmented reality skinning, I take what I used to have, and I'm going to put different types of textures on it. Some for floors, some for walls, some for ceilings. Now I look like I'm in a different space. So in this last demo, what we ended up doing is whenever we updated scene understanding, we would take the floor and we would ask Unity to generate a nav mesh out of it. And then we plop this character on it and had it navigate around. So this is now going to be large scale navigation in my space. So I'm just going to ask it to go on the couch. And then another part of my couch, you notice it kind of walks on the couch itself. And now I'm going to use a follow command where it's just going to start coming at me wherever I am. So it's coming, and as you can see, when I walk around things, it actually reroutes to attack me. And again, like, it has mapped out my entire floor. So to demonstrate that, I'm going to try to walk and run away from it. And it'll just follow me wherever I go. I'm going to do it one more time here. And it's a little bit surreal when you do this, and a little creepy, but kind of fun as well. Yeah, so here it is. It's like creeping around the corner, and I'm actually going to go outside, and it has no problem. It just follows me around. So you can see that if you have written applications that have characters that can walk around nav meshes, you can suddenly just take that code, incorporate it into scene understanding, and you can have an AR version of that same application. First, let's take a look at a high-level architectural view of the scene understanding runtime, so you can understand where your application interfaces with scene understanding and how it relates to spatial mapping. On the left, you'll see there's something called the HoloLens sensor runtime. Think of this as the sensor driver where you've interfaced with environmental data in the past. You can see that HoloLens sensor data is sort of streaming into the device as you're walking around. And both the spatial mapping and scene understanding runtimes are taking this data and processing it all the time. This is why you don't need a pre-scan in scene understanding or spatial mapping. You don't turn it on or off. It is just accumulating data and learning about your space. Now, in the case of spatial mapping, if you've used it, you use windows.perception.spatial.surfaces to pump mesh data to your application, and you can do that directly. Or people use MRTK or OpenXR wrappers to make it a little bit easier. On the scene understanding side, so I'll highlight the block here. So this is the scene understanding block. It is doing a similar thing, but rather than talking directly to the API, which is very dynamic and high level and hard to encode, instead, what you do is you download the scene understanding SDK, which I'll highlight here. And its purpose is to both talk to the scene understanding runtime and get scenes for you to process, but also to create an abstraction layer that makes it much easier for your application to understand these high-level constructs. One thing that's interesting too is, and I'll draw it here, is this scene understanding data. So when you make requests for scenes using the SDK, there is a protocol that is used to send this information back and forth. And we can save this to disk, we can serialize this and use it later. And you'll see, serialized scene files that are, saved as part of our sample, for example. And they can be useful for other things. You can capture your space and reload it later. So rather than hide the fact that we have this communication channel back and forth between scene understanding and the SDK, we specifically want you to look at the data that is being passed over the wire and do interesting things with it. So you can't really do all that much with scene understanding unless you actually have a scene. So the very first thing you're going to want to do is request one. The request is comprised of two parts. You first define a query settings object that tells the runtime what data you want it to compute. And then you make a request and it will return a scene for you. And the scene will be an immutable snapshot of your environment at a particular point in time. By immutable, I mean that the data in the scene are not going to change. You can query it, you can look at it, you could request a new snapshot. That object will remain static. So let's walk through how this works. First, you create your query settings object, and you set it with some parameters. So in this example, we said, hey, we want quad object, we want all the meshes, we want you, this set is false, which means we actually want you to infer everything and use the power of AI to define what's under tables and find the watertight meshes, etc. We want to enable this spatial mapping mesh, and not only that, we want the finest level of detail possible. So this is sort of give me everything mode, and we call compute async. And this parameter 10 right here says that I want to get everything within a 10-meter radius of my environment. And what this will return is a scene. And this scene is now parsable by the SDK. If later on I want to get a updated version of my scene, we said these are immutable, so nothing changes. So how do I know if my wall data is updated, if my, I got more information about my scene, how do I get more information? So what you can do is you can call the same function again, but this time you call it and you pass in the previous scene, and what you get is a new scene. It's immutable once again, it will never change, but now this scene has been generated in the context of the previous one. So all the IDs of your objects remain the same. So what is this scene object that you get? This diagram illustrates the structure a little bit. So at the very top, you have your scene object. This is the root, and it is represents the snapshot of your environment. It's comprised of just two things, an origin and a list of scene objects. Now the origin is actually very interesting. If you're working in traditional 3D applications, you're used to having a coordinate system for your objects that is shared by all. But in the world of AR, that is not a luxury that you have. You are working in a dynamic world where you have multiple coordinate systems, and your table and your floor are not necessarily attached to the same coordinate system and can move independently of each other. But because scene understanding takes a snapshot, we can snapshot it all relative to one anchor, or one origin space. It's interesting when you go to render these objects now, because you can choose to render your whole scene anchored to one origin, or you could take every scene object that you have and anchor it specifically and make it basically turn it back into this bendy world. And depending on the application that you have, you make those choices. But it's presented to you as a single static thing so that you can reason about it in its snapshot space. Then you have your array of scene objects, and scene objects really define things that you have. So they have a kind, it could be a floor, a wall, the world, something else. They have a transform, so it means that like the thing has a position in space. That transform is relative to the origin of the scene. And they have IDs in the forms of GUIDs, and the IDs are there to preserve this flow of time. So when you update your scene from a previous scene, an object will share an ID. So if you had an object, of ID 5, that was your wall, and you updated your world again, you will look at, the object of ID 5. It'll be that same wall. It may have moved, it may have changed its properties, but you can sort of find it again. And this is where this ID system takes place. And lastly, the last part of this is this notion that these scene objects are represented by many things, potentially. So they can be represented by meshes, that's the scene mesh on the left, by collision meshes, or quads, and we'll talk about the difference between those later. But I hope that the former are sort of clear in the sense that, yeah, you have these geometric representations, and you have multiple representations of the same thing. Just like in Unity, you could have a collider for your object, and the mesh of your object. They are represented as two different things, and stored as two different things. We sort of mimic that space as well, and you can use these objects in that very same way. In this section of the talk, I want to present some common developer patterns that we've experienced when working with scene understanding. The first one involves an application that has some sort of understanding of the environment encoded in its native engine, either Unity or Unreal, with characters or physics or whatever experience that you have that needs to interact with it. And so all we require is that when a new scene is computed by the scene understanding runtime, we have a way to map it to some objects that are native to that engine. So here's an example that I've presented as a toy example. On the left, we have this scene. It has an origin. It has a bunch of scene objects, a wall, floor, and a world, for example. And then what happens is on the Unity side, when we get this new scene that comes in, we create this new set of objects that mimic what we saw in scene understanding. And in this way, we keep the real world aligned with the simulation, tracking it over time. Now this should be a little bit clearer as I highlighted all the pieces that map between your scene understanding scene and your Unity scene. You'll see that not everything is in the exact same place. So for example, I've kept the IDs for all the objects, but I've encoded them in the names of the objects instead, because there's no place to put them in Unity. I've decided to ignore the quads for this example, but I've kept the meshes and collision meshes and converted to meshes and mesh colliders. And I've pretty much assembled it to match, the two. And at this point, I can pretty much discard what the scene understanding scene generates for me, and my application just deals with this environment as if it was virtual. One thing that is interesting too, again, we will want to render this scene and align it with the real world. So we have to do that somehow. So don't forget that the origin encodes an anchor, and there are Windows APIs that allow us to get the transform in Unity that map anchors to positions for the system to render them. I didn't put a lot of the code here in this slide. If you go to the sample, you'll see how we do this, and you'll get a better sense. But this will essentially now encode your scene into your engine and render it correctly. Well, it's interesting to map our 3D world to 3D environments. 3D is hard. If you remember, our mandate was to make it as simple as possible to interact with environments. And we have to acknowledge that a bulk of the applications that we write are 2D in nature. Maybe in augmented reality, they'll be 2.5D. And we really want to make sort of 2D a first-class citizen of the augmented reality space. If you're sitting at your desk and you're looking at a monitor, you have windows on that monitor. They have a location in 3D, but because they're physically located near you. But the engineers who built it were only thinking about it as a 2D slate, as a 2D window. And we've introduced quads to be that 2D representation. We want to take any flat, planar surface and convert it into a virtual canvas or a virtual window that you can write your applications on. So in this example, I have this room and it's got some stuff in it. And let's take a wall and turn it into one of these quads or this virtual window. So first I'll highlight it, and it's quite easy to see how this nice rectangular thing can become this rectangular object onto which I can start to draw or put content. But clearly, this is not the real world is a little bit messier, and we saw that there was a window and a shelf. So quads provide this information. They have regions that they define that tell you where they either don't exist or you cannot render content. So in this case, there are two such regions. One is an invalid region that says, hey, there's a window right here. It doesn't say there's a window specifically, but it says like there's a hole in this wall. So you simply cannot draw any content here unless you really want to. And there's another section, this green section, that says, hey, I haven't really seen this area, so there might not be a wall here, but you can do something if you find it interesting. Now, clearly, still, this wall was rectangular. You can imagine if this was put on a table, like a circular table, there would be red regions, outlining the shape of the table as well to tell you what part of this rectangular space you can actually draw on. And now you sort of have like the closest thing you could get to a rectangular representation that happens to also align with what is going on in the real world as you've scanned it. So if you've never done it, you might think that placing a hologram on a 2D surface is an easy thing to do. You have to trust me, it's not. And that doesn't even take into account the fact that you have this complicated case where you have a window that cuts a hole through your wall and you have a shelf that covers it. So I'll walk you through how you would do this in Scene Understanding. First of all, I'm going to assume that you've used the pattern that we presented before. If you download a sample, it just does this for you, where you have your object of your wall that's localized somewhere in space. At this point, interacting with the wall as a canvas essentially means that you just route your object to the wall. So it inherits all the transforms, and you do everything in X and Y space. So luckily, if you want to do placement, you can use a function that we've provided called find centermost placement. And it does exactly that. It'll find the XY location to put your hologram so that it is in a good spot. Now, like in this case, this is not going to be the center of your quad. Because again, like in the center of my quad here, I have a window, so that's not very valid. So we'll see what happens. So I call this find centermost placement function, and I pass in here 0.2. This is the extent of my object. So I tell this API how big my object is, and it returns pause, which is going to be a 2D location on the quad. Next, I'm going to take my clock object, which is my hologram that I want to place. I route it to my wall, and I make my transform, this pause X, pause Y. All is a 2D thing. And what will happen is magically my clock will appear on the wall exactly where I may have wanted to do it. If I want to place it somewhere else, there are APIs that give you the regions, invalid regions, and you could compute something a bit more clever yourself, but we at least provide this handy utility so that you could solve this most basic task very, very easily. The last example I wanted to walk you through is this process of taking a 3D representation of your environment and projecting it more easily into a 2D representation. This is used if you want to create a mini map or a floor plan generation or even some basic room analysis. It's very convenient to try and take this 3D world and combine it to a 2D world. We won't walk through all of the code, but I'll show you some key concepts that might be interesting. So the way I like to write this application is to use the largest floor in the scene as a 2D canvas. And so my application has sort of 3 stages to it. The first is finding the largest floor, then finding a transformation that will transform it into 2D, and then to project whatever I want to project, so in this case all the walls, onto the floor by taking the inverse transform for that floor and projecting all those objects onto it. Let's walk through how that works, and hopefully it becomes clear. So the first thing is this find largest floor function. How would I do this? This is sort of where, to me, there's a magic of both scene understanding and how link works in C#, where I can start making what seem like much higher level requests for things. So how do I get all the floors, for example? Well, I literally call scene object.where the scene object kind is scene object kind floor, and I get a list of floors. So this is like a nice query. I just say, hey scene, right? Give me all the floors, and it gives them to me. Then this is a fairly simple for loop where I find all of the quads of the floors, and I say, hey, I compute the area and compare it against the largest area I've seen so far, and I remember the largest floor, which I do here. And when I'm done my for loop, the largest extent of the largest quad is my largest floor. It's really simple. Then I want to compute the matrix. So why do I want to do this? So from some very basic refresher, the transform of the floor is going to tell me where the floor is in 3D space. If I invert that transform, it is essentially going to put it into like a 0, 0, 0 coordinate system, where x and y is the is also like the quad x and y, and z can be ignored. So I find first the transform. So there's a function get location as matrix. It gives me the transform, and I call in the matrix 4.4 invert function to invert the transform, and I have my transformation now. I'm not going to walk through all the code that finds walls and projects them, but the very basics are that I again sort of call a new query where I ask now for all the objects that are kind wall. So I do this here. I have all the wall scene objects, which I'll highlight, and I iterate through all of them. And this is the sort of key line right here: transform to floor up space, and that is essentially the wall transform times this inverse floor transform. And if I take a wall and I transform it here, it will first put it into the real space and then invert it into this 0, 0 space, and you have to believe me that all the vertices now, if I ignore the z height, it's a 2.5D transform. If I ignore the z height, they will all project nicely into 2D. And this is where I do this right here, where I transform the position of each point on the wall, and I have my 2D points. That's the bulk of our content. If I've done my job correctly, you have a good sense of what scene understanding is and why we built it. You might have some ideas of things you might want to try. Hopefully you understand how applications interface with scene understanding, and you have a general sense of how the code might work and how the flow might work and some patterns. The next step really is to start playing with it, whether you want to do great code or really just experience it. And this is why I point people initially just to download the sample. The sample is built in Unity. You have a link here that you can click on. It's built in Unity, and even if you don't have a HoloLens, we include a serialized scene. You just uncheck the Run on Device tab, press play, and you can start navigating a sample scene that we've built. I really encourage you to do this. If there's a value to the community, we can actually produce more, because we know that HoloLens 2 availability is one of the barriers of experimentation. But there's really no reason to not use scene understanding if you don't have a HoloLens, if you're interested in it. And we could very well produce more scenes if the community asks for them. But you can explore the SDK, you can play around with things, you can look in the code, you can modify things. A lot of the demos that we've produced to you, we will start to integrate back into the sample, so please keep checking it regularly. Once you've done that, and if you want to know more about how to write code for scene understanding, I link the SDK reference. There you can browse and learn more and get more details. And then finally, we are working on integrations with MRTK, so you'll be able to access scene understanding directly through that. Although it's still valuable, I think, to learn the SDK, because you'll always have the choice of using MRTK extensions or to get more power to sort of access the SDK alongside of it. This is something that works just naturally. And then finally, we're also working on OpenXR extensions as well, so look for that in the future. So I would be remiss if we didn't mention MRTK a little bit more before we finished for today. If you were to click on the link that I presented in the slide previously, you would be taken to this page. This is the PR for the official integration of Scene Understanding into MRTK proper. We will be integrated officially in upcoming release, but you can take a look at the PR, integrate it, and run it. I'll show actually a video so you can see what it looks like. There's a panel that you can see that allows you to change various settings, and you can see it's directly integrated into the rest of the runtime. I encourage you to try it out if you're an MRTK developer. I also encourage you to experiment with Scene Understanding and MRTK together. There is no reason why you can't use the power of MRTK and then use the SDK as well to augment your worlds and environments. So there's many ways to use what we've built. I'm really looking forward to seeing what you do create. So that's all the content that I have for you today. I hope it was interesting. I hope it was entertaining. And I really hope that not only have you learned something, but that you leave this space thinking, okay, this is awesome. This is what I want to use to start building augmented reality experiences, but that I want more and I have ideas. As I mentioned, we built this runtime for you. We built it for the creators and developers because we really believe that we need runtimes such as this to maximize what augmented reality can do. And we don't want this to be a presentation of like, this is what we built and this is what you should use. We really want this to be the starting point of a conversation where we learn what you need from us. What does a runtime such as this need to do in order to make sure your idea comes to life? So I hope we can make use of forums such as these and any other means in the future to really drive the features and the needs of you, the developers and creators, to create the most amazing augmented reality experiences. So with that, I want to thank you very much for listening, and I'd love to hear your questions. Thank you.